Hello, I'm Omnik. Today I will be solving educational code first round 168, and I'll try to explain what I'm doing. Why in education rounds there is no list of problems on the right side, like usually they're here, right? Okay, so we have a string of lowercase letters of length at most 10. Current password is too weak. Insert exactly one lowercase letter to make it stronger. The password strength is proportional to the time it takes him to type the password. Time to type the first character is 2 seconds. Which character other than first? The time it takes 1 second is it if it is the same as the previous character, so 2 seconds otherwise. Okay, so basically the time is 2 times length minus the number of consecutive pairs that are equal. So we want to minimize the number of consecutive pairs that are equal. And obviously we can always insert the character. If we choose the position where to insert the character, we can make sure that it is not equal to the previous or the next. Because there are more than 2 letters in the alphabet. So we just want to choose a place to insert which will reduce the number of consecutive pairs that are equal, which is between 2 equal letters if you can, otherwise somewhere. So that's it. So if this character is equal to the previous one, we would like to insert and I'm not sure how the function insert works, but like let's say like this. Insert something between them, and if they're equal, then insert something else, and that's it. Otherwise we will just insert something in the end, and if okay, let's insert in the beginning because it's easier to access first first characters and the last 2 characters. No much in function insert. Is it like this? Oh, I should have set as the begin here, right? Oh no, it doesn't like this one. Okay. So is it like this? Okay, in problem B, I guess we'll be working with this grid 2 by n. Cell is either free or blocked. Free cell is reachable if it is reachable by sides. So by for connectivity, connected region. Yeah, it's connected component. Okay. The given grid contains at most one connected region. That is to calculate the number of free cells meeting the following constraint. If this cell is blocked, the number of connected regions becomes exactly 3. So if there are no connected regions, it means that everything is blocked and the answer is 0. Oh, there is even sample like that. Okay. Otherwise, like everything is one connected component, but if we block a cell like this, like it must have 3 neighbors, obviously, and then those neighbors must be not connected in any other way. So this cell must be free, but these 2 must be blocked, so that this one will be one component, and then we have one on the left and one on the right. Alright, and those 3 must be free. So we're looking for a number of like rectangles 2 by 3 such that it's free, 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 and blocked, blocked. Then this cell is the one we want, and symmetrically, obviously. there is not much to explain here, just checking for this particular pattern. Problem C. Have a regular bracket sequence of even length n, calculating the cost. Each opening bracket is paired to the corresponding closing bracket, so the cost is the sum of distances between pairs of corresponding bracket pairs. Okay, sure. Unfortunately, due to data corruption, lost all characters on odd positions, only characters on even positions remain. Wants to restore, wants to choose one with minimum cost. Well, okay. So basically we want pairs of brackets to be as close to each other as possible, which kind of means we don't want to have big balances. Like all the balances should be non-negative, obviously, but like I'm pretty sure that this function can be calculated as like sum of balances, probably like exactly sum of balances. So in this case it's 0 1 2 1 0 1 0, and the cost will be 1 2 1 1, that's 5. Yeah, well, why is that? Well, because pair of brackets adds to balances, well, between them, plus 1 between them. But that's exactly how much it adds to the score. So the score is counted as sum of distances between parent brackets. If we take parent brackets and add 1 to every point between them and then sum up those values, we will get the same sum. But those values are balances, as we are used to, like, determining whether the sequence is balanced. So I want to say that we should just go left to right and greedily set the next character to have minimum balance. So basically, set closing brackets if you can, if that doesn't make balance negative. Since our balances like each time we need to make a decision, our balance is non-negative and even. So if it is 0, then we must put opening bracket there. If it is non-zero, so it is at least 2, so we can put closing bracket, then we will have something that is already there, and maybe the balance becomes 0, but it cannot become negative. And it's always good to reduce balance right now. It doesn't make sense to increase the balance to decrease it further. So yeah, just do the greedy, and we need to print the cost. Okay, and it might seem that the cost is like O(n) squared, and for general bracket sequence it is true, but we will never have balances greater than 3, so the cost must be bounded by 3n, which fits in integer. even positions, because we are in zero indexation, we need to make the choice, and if the balance is 0, then we put an opening bracket there, otherwise the closing bracket. If we have an opening bracket, then we increase the balance, otherwise we decrease it. We can assert that it is not negative and add it to the answer. And here we can assert that the balance is 0. Well, I think it should be guaranteed that the last one is the closing bracket, as can be restored to at least one regular bracket sequence. Problem D. You're given a rooted tree. Plus the root is vertex number 1. Value AI is written at the is vertex. You can perform the following operation any number of times. Choose a vertex V which has at least one child, so not a leaf. Increase AV by 1, decrease AU by 1 for all vertices U that are in subtree of V except V itself. However, after each operation, the values on all vertices should be non-negative. Okay, so we can like suck the life out subtree to increase the value in the root by 1. Kind of seems cruel and pointless. Your task is to calculate the maximum possible value written at the root using the aforementioned operation. Okay, it kind of looks like it is like the order of operations doesn't matter. Like in the sense that, well, it does matter because we cannot make values negative, but I want to say that if we can look at some set of operations, and then if we want to make this set of operations, we can go from lowest vertices to highest and do in that order. And then for the set of operations, the final picture does not depend on the order, because for every vertex the value is just like initial value plus the number of times we did the operation in this vertex minus the number of times we did operations on all the ancestors, because like that's when we get -1 and +1. So the order doesn't matter, and we can see that for every vertex we first do all the operations that do +1s, and only then all the operations that do -1s, because we go from lower vertices to higher until we reach the root. And so also when we if we like go from lower vertices to higher, once we like leave some vertex, so we know that we will not do any more operations inside this subtree, then all the operations we do higher or like on the side either do not affect this subtree or they do -1 to all the vertices in this subtree at the same time. And so for this subtree, the only thing that matters is we cannot make any numbers here negative. So actually, like the characteristic of this subtree after we leave it is just minimum of values. Like, and that is how many times we can do the operation like on the ancestors. And so we should be able to do just like DP, where we don't choose anything, we just calculate the values. For every subtree, we calculate what is the largest number of operations we would be able to do on this subtree once we leave it. So first we do operations somewhere on this subtree, like inside, and then we go here, and then like in the root of this subtree, we did some operations. Now this subtree has some values, and we are only interested in minimum of those values. And we want it to be as large as possible, obviously, because we want to be able to make more operations higher. And so the DP value of this subtree is what is the maximum possible value we can get here. And how to do this? Suppose we calculated it for all the suns. For leaves, it's just the initial value because we can't do any operations in the leaves. Then look at the vertex. Suppose we calculated for all the suns. So we know the values, like maximum possible value of minimum in all those subtrees, and we have some number in the root. Now we can choose some number k and increase the value in the root by k while decreasing all of those other like lower values by k. And the minimum of them will be the answer. So to calculate the value in vertex v, we will just take values for the suns, take minimum of them, and then we have value in the root, we have minimum of values in the suns. If the values in the suns minimum is smaller than this is the answer, we cannot increase it. We can only decrease it, and that's stupid. But if the value in the root is smaller, we can increase it by decreasing values in all the suns, and the answer, the best minimum we can get is like we have smaller value in the root, we have larger value in the suns. We can like increase this one by decreasing this one. So we need to like make them as equal as possible, and the answer will be just like their sum divided by 2, rounded down because we can only get integers. That's it. And the value we will calculate for the root is the answer to the problem. If you give the tree as like list of parents, please make sure that the parent has smaller index, so I can instead of writing DFS, I can just iterate from the end, from the leaves to the root, just right to left. Now I have to actually write recursive DFS. Values and parents. if I'm not mistaken, and I think that I'm not, we cannot ever get values greater than the bound for initial values. So if all initial values are bounded by a million, we cannot get, or not a billion, we cannot get dp values greater than a billion, so I can get infinity that is greater. So if x is infinity, it means that our vertex is a leaf. We shouldn't do anything, otherwise we will compare the value in our vertex with x, and if it is smaller, then we replace it with sum divided by 2, otherwise we replace it with x because it's smaller. That's it. Oh, right. So, yeah, it doesn't make sense to increase the value in the root of sub3 higher because we will not be able to use it later, but if we don't need to use it later, yeah, we can do that. So like after I did this, I have like my current value and value of like minimum over my sums of dp values. If I would like to like continue doing this on the sub-tree, it only makes sense to make them like almost equal. But if I only care about what will be the value in the root, and I can just murder everything that is below, so I should like print my initial value plus the minimum over sums. So instead of doing this, we will like iterate over all the sums of the root and calculate the dp's there. Actually, I don't need to store the parent, right? I have a directed tree. N is at least 2, so it is guaranteed that like there is at least one sum of the root, so x will not be infinity here. Problem E. Playing computer game. starts the game being level 1. He's about to fight n monsters in order from 1 to n, so we can't change the order. The level of each monster is a I. For each monster in the given order, the encounter goes as follows. If our level is strictly higher, the monster flees, otherwise we have to fight. After every case fight with a monster, fleeing monsters don't count, Manakapa's level increases by 1. So his level becomes 2 after k monsters he fights, 3 after 2k, and so on. And to process Q queries, will Manikarp fight the is monster if the parameter k is equal to x? Okay. Mm, 4 seconds, 200,000. Well, the problem kind of screams some kind of squared decomposition. Basically, because if the value of k is small, like smaller than the square root of something, of n probably, then there are just small number of values of k, and we can for all such values of k, we can just emulate the process in linear time and store all the answers. And if we will be asked to solve for this value of k, we just know all the answers. But if value of k is bigger than square root of n, that means that our levels are small, because like we start with level 1, and to get to level like d plus 1, we need to increase the level d times, which means fighting d times k monsters. So d can be at most n divided by k. And if k is greater than square root of n, that is square root of n. And so like for big k, it is kind of tempting to like try to understand fast. Like, so okay, we start with level 1, we will fight everyone. So we just need to understand which monsters will run away. So our level must be greater than their level when we arrive to fight them. So we start at level 1, now we fight everyone. So we just we want to understand when we will level up. Well, that will happen after k fights. So come on. After k fights, we have level 2, so all the monsters with level 1 will run away. So we need to ignore them, and we need to find the first place where we need to jump k. Jump to the first place where we actually fight k monsters. So find the first place such that on this segment there are k values that are at least 2. How to do that? Well, we know that we will ask those questions, like for we know the left border, we know the value of k, and we know the values smaller than what we ignore, and that last parameter, what values we ignore, it is up to square root of n. So for each value of that parameter, we can calculate like our own prefix sums, like prefix sums of count of the number of monsters with level at least this. And what we want is, for this left border, we know the current prefix sum. We want to find what is the first place where the prefix sum is z plus k. So let's store for every value of prefix sum, let's store the first place where it is like that. So for every like bound on values that we ignore, of which we have square root of them, and for every prefix sum up to n, we will store what is the first place this prefix sum occurs, and also we will store the prefix sums themselves. Then we can emulate given value of k in O of square root by saying, okay, we start here with level 1, find where we will have level 2, jump there, that jump is at least square root, so there will be at most square root of n jumps. Now we have level 2, find where we will have level 3 by looking up at the table, like we know the current prefix sum if we ignore all smaller levels. So we know current prefix sum, we know what prefix sum we want. We have stored where it first occurs. So we jump there. Now we have level 3, look up those values, do the jump, and so on. And so we can emulate all of that in O of square root of n. And that's it. So values of k that are smaller than square root of n, we just emulate once in linear time and store everything. Like just for every value of k, store for every monster whether we fight it or not. For values larger than k, we have pre-calculated some smart lookup tables that allow us to implement what will happen for that value of k in O of square root of n. And for each query we will just do that and answer the query that we want. Do I have enough memory? Yeah, I do have enough memory. That's cool. Okay, so 500 is greater than square root of maximum of n. So what do I need to store? So like for small values of k, for that value of k and for every monster, whether we kill it or not, we can, for example, store bit set actually to use less memory. You can store just one bit. Then for ignoring values that are smaller than 1, 2, and so on, like up to square root of n, we need to store prefix sums, and also first occurrence of given prefix sum. Alright, so for every k smaller than our bound for square root, just implement what is written in the statement and store all the answers, whether we find each monster or not. So we'll say our current level is 1, we'll run left to right, and we need to store like what is the number of monsters we need to kill like until next level up, for example. So it is k. We run left to right. If level of current monster is smaller than our level, we don't kill him. So don't do anything. Otherwise, we remember that we do kill him. We decrease left to kill, and if it reached 0, it means that we have level up and that counter is set back to k. That's it. So we remembered all the information for small k. Now for the second part, when our level will be small, so let's say that our level is m, and we ignore all the values that are smaller than m, we will calculate prefix sums and store the first occurrence of every prefix sum. So those are the prefix sums. So now initialize all the first occurrence with some dummy value like -1. And if we run right to left, we will look for every occurrence. The last value we write like here for this value will be the leftmost position where this prefix sum occurs. All right. So now we will answer the queries. Each query is position and value of k. So if k is smaller than b, we just know the answer. We calculated it already. So on the sample, this should already work because all the values of k they will ask are small enough. Yeah, that looks correct. Alright, but like in reality, we need to solve this still. Alright, so to solve it, we'll say, okay, let's emulate what will happen for given value of key. We start with level 1, we start in position 0. And we will try to find the next the position where we have level up and so on until we reach this position, and at that point we will know our level and we will compare the level of the monster on position P and our level and say whether we will fight it or not. So how to do that? Okay, we know our level. We can say assert that our level is smaller than B. That should be true. And well, this will be a valid solution even for a small k if our level will stay smaller than B. So the problem with small k is that level can become big. But technically this would still work, assuming that this assert still holds true. Okay, so our current prefix sum is, well, prefix sum that we stored for this level and this position. So we need to kill k more monsters, so the prefix sum we need is k bigger. Here we need to be careful because like if k is very big, we could get numbers that is greater than our limit on the size of this array. So let's create like what is the position where we will have this thing, and if x is smaller than big N and this first occurrence of prefix sum x when we calculate it for level LVL is not -1, so it actually occurs, then this position will be first occurrence. Also, let's make it like big N or something. Now, if P is smaller than, so this is basically infinity, and like we have found where will be the next position where we will level up. If it is like big N, it means that we will never level up. So now we want to check if is it true that the position that we are interested in, position P, will happen before the next level up. So this is the thing we want to ask. And if it is true, then when we arrive at that monster, our level will be equal to this level. And so if our level is smaller than P, then the answer is yes. Otherwise, no. And we break. Otherwise, we know that P is at least this position, which means that it is not infinity. And so we say, okay, then we like jump to this position and get our level up. That's it. So we should never arrive here now, but we can say, okay, those are the correct answers. But actually, this part of the solution should also work, because like this assert still is true. So we can comment this part and check if the answer is still the same. Memory limit exceeded. I thought that's a lot. Okay, let's calculate it actually. So this is like 10 to the 8 integers, and I have 2 of those, so that's 800 megabytes. That's not great. Okay, so considering that for this thing I only need 1 bit for every n, and here I need 2 integers, so that's like 64 bits. I should like make it uneven, right? So I will say that b is like 2000, and this should be like n divided by b plus epsilon, and make this to big M, and this also up to big M, and this assert is to big M. Alright, so now this is 400 million bits, so it's 50 megabytes. And this is, so M is like 100, so it's 40 million integers, which is 160 megabytes. So this whole thing should take like 210 megabytes. Alright, let's read problem F, and then we'll check my calculations of memory. You have n chips. I'm going to place all of them in one of x points numbered from 1 to x. There can be multiple chips in each point. Okay. After placing the chips, you can perform the following 4 operations in any order, any number of times. Choose a chip at point I at least 3, remove it, and place 2 chips, one in I-1, one I-2. So it's like, if we imagine as like stacks of chips, we take 2 and move them there. Okay, choose 2 chips in adjacent points y and y+1, remove them and place a new chip in y+2. So that's those 2 are like back and forth, and those also back and forth. Okay, chip and point 1 move to 2, choose chip point 2, move to 1. Okay. Now that the coordinates... Oh, that kind of looks like Fibonacci system, right? Like 1 and 2 are just both ones in so like first Fibonacci and second Fibonacci are just ones, so they're interchangeable, and is Fibonacci is equal to the sum of two previous. So basically this thing describes like storing a number as a weighted sum of Fibonacci numbers, and we can change the weights so that the number is still the same. So we can like interchange 1 and 2 weights, that doesn't change anything, or we can like take a weight in some I at least 3 and replace it by two previous one, or we can take two consecutive and replace them by the next one. Okay, so this is kind of like Fibonacci like numeric system, like storing the numbers weighted sum of Fibonacci numbers. The coordinates placed during the operations cannot be less than 1, but can be greater than x. So we start only from 1 to x, but they can get further away. Okay. Note the cost of chip placement as the minimum number of chips which can be present on the line after you perform this operation, starting from the placement you have chosen. So the placement we have chosen just describes the number that is stored in this Fibonacci system, and then we can write it as we want. I'm not exactly sure, like so there is a Fibonacci Fibonacci-based system that says that we cannot have two consecutive ones. And well, obviously it doesn't make sense to have two consecutive ones because we can take them and replace by the next, but also all the digits are just zeros and ones in that system. That's not super clear that this is the most the best system. I guess like if we have two somewhere, we can replace this one by two previous, but then take this two and replace by this. So if we have two, we can split them in like one here and one here, and that's not worse. So I guess making it a Fibonacci number system is the cheapest. So the cost of chip placement is just the number of ones we would use to represent the same number in the Fibonacci number system. Right. Given an x, num calculates the number of placements of exactly n chips in points from 1 to x having cost equal to m printed modulo. Okay. So x is up to 10, and 10's Fibonacci number is not very big. It's like 89 or something. So the biggest number we can get is like 89,000, maybe even smaller than that. 1, 1, 2, 3, 5, 8, 13, 21, 30. 55. So 55,000 is the largest number we can write. So we should just calculate for every number up to 55,000 in what number of ways we can like place chips to get that number, which is just like simple knapsack DP, right? And then for every such number, calculate how many, like what is the cost. And that is done by greedy. You just like take the largest Fibonacci number that is not greater, and subtract it, and do that until you reach 0. The number of iterations you did is the number of ones you would need. Okay, that's it. That's the solution. So the whole problem is about just understanding that this thing describes Fibonacci number system. And well, since I can read, I understood that, and the problem is solved after that. That's a cool lesson in reading problems. 210 megabytes. To the point. It's nice. Okay, let's implement that. That's a cool problem, actually. I'm not saying it's a simple, stupid problem, and no, wait, I want mint. Don't want those old thingies. Alright, so well, let's check my calculations. So start with a fun of 2 equal to 1. Right, so F10 is 55. So the maximum number is 55,000. I have calculated much more than that. So now we want to DP. So I want to place exactly n chips. So the placement of the chips is described by like how many chips you place in every position. In total you should place n, but that means that we can like describe the same as going left to right and writing the position of each chip. In the end we will get the sequence of exactly n numbers from 1 to x, where x is up to 10. This sequence should be non-decreasing, and we are interested in like what is the number that is represented by the sum of those Fibonacci numbers. So our dp will be like so what is the current number from 1 to x that we are staying on, and the operations we can do is increase the current number by 1, so like we stopped putting number t and start putting number t plus 1, or put another chip here in position t, and the number of times we put something should be exactly n. So okay, we start at saying that the current number is 1 and the current position we're staying as 1, and the current number that is sum of corresponding Fibonacci numbers is 0, so we have one way to achieve that, and we will have n iterations of this cycle, and after each iteration we should put exactly one chip. So first we will allow ourselves to move to the next position several times. Maybe it's okay to skip some position and not to put anything there. So to do that we will say okay, like this. And now if we are still staying in position t, and our current number is x, then we need to move from x to x plus Fibonacci of t. I guess I will need NDP. Or I can just say like x plus f of t to n. So yeah, I'm a bit lost in this dynamic programming. So normal. The problem is that I want to like not store the parameters that says like how many chips we have already placed, because like otherwise I will not have enough memory to store all the DP values. So I have already like, inside my mind I have already eliminated that parameter. and only storing like last layers, but when I'm trying to explain it, it's a bit clunky. So the actual dynamic programming should be what is the current number of chips we have already placed, what is the current position we are staying right now, and what is the current sum, and the transitions are either move to the next position or place one chip in the current position and change the sum. But because I don't want to store that number of chips, I'm only storing the last layer byte, and then I'm separately doing the transitions that are inside one layer when I'm only changing the position. It's here, like from this state, I'm moving to the state with like the next position. And then I'm placing the chip. So I'm staying in position T, my current sum is X, I will add Fibonacci of T to that position, and I'm moving to the next layer now. And now I'm copying the next layer to the current layer and zeroing out the next layer to not like reuse the values that I had before, because I don't want that. Alright, so I have calculated the dynamic programming. It works in time like n times 10 times the maximum sum I can get, which is 1000 times 10th Fibonacci number. So in terms of like input values, it's n squared times x times Fibonacci x, which is just 55, but like in terms of dependence on x, it's exponential. So if x would be like 20, it would be much bigger number, and if x is 100, it would be like it would not fit in long, I think. So it's exponential of x, but the actual maximum limit is just 55, which doesn't seem like that big. Okay, now we will iterate over all those numbers, calculate the number of ways we can get it, because it is not stored anywhere in our DP technically, because our DP also stores the current position, which is irrelevant now. So we just sum up over all the possible positions to get this number. So this will be the number of ways to get x, and now we just check if the number of digits in Fibonacci system of x is equal to m, then that's the number we want, and we need to add this count to the answer. And to write this function, oh, I reused m. That's not great. Just greedily put it in So to find the representation with the smallest number of chips, we're saying, okay, it's the greedy one. So if we want to represent number x, we just find the largest Fibonacci number that still fits in x and put one chip there, basically. Yeah. I will not prove right now that it is optimal by the number of digits. Let's say that it's well known. What so slow? Well, okay, I guess it's because like, this is such to be. I don't know. Like this is just 1000 times 10 times 60,000, which is 600 million. There are no like, multiplications or divisions, so it should be fast enough even on 32-bit system. That's not great. Well, okay. Wow, I lost the jungle only by 23 minutes while explaining the solution. Okay, sure, that's cool. Alright, thanks for watching. Bye.